Okay, so let's keep going. We have to talk about ergodic theorems. And again, if you still don't have access to the Fields LMS, you send an email to Shuchan and he will add you. So is there anyone who has that problem? That no, some people have been added. Okay, so what are ergodic theorems? So we said that the setting, in general, the setting would be that you have a measure preserving system, so a set, sigma algebra, probability measure, and transformation. So this would be a measure preserving system. And we have so there's two types of theorems. So the first two theorems of von Neumann and Birkhoff have to do with a function from X to R, which is usually called an observable. Okay, and so recall that whenever you have an observable, you can define the Birkhoff sum. Which is just SNF, which is just the sum of F composed with T along the orbit. So usually, traditionally, we start with time 0, meaning F of today. We don't apply T to n minus 1 to make sure that there's n terms. Okay, and so the classical ergodic theorems tells us that there is a limit. If you take this sum divided by n, there is a limit. So there's still a so the von Neumann theorem, which we discussed last time, without really complete proof, but more or less give an idea, is that if F is in L2, then there exists F tilde, F bar, which is invariant such that F bar composed with T equals F bar, also in L2, such that S and F divided by n converges to F bar in L2. So this is the first earliest ergodic theorem, which, as I said, has this nice interpretation in terms of projection in this Hilbert space. So L2 of XP is a Hilbert space, and the space of invariant functions is a subspace, as I said. So of course, there are many theorems of this flavor. So this is L2T, and the whole thing is L2. The flavor is that you take a point, because this is 0, you take a vector in the space and you project down. So this is F and this is F bar. So this is nice because you have this geometric interpretation. Now, if you go to L1, well, it's a bit less geometric in the sense that in a Banach space, then okay, the orthogonal projection is not always the word orthogonal doesn't mean much, so you can define maybe a projection, but it's a bit less transparent. But the same theorem holds, and in fact, a much better convergence holds, which is almost sure convergence. So the Birkhoff theorem says the following, that if you start with F in L1, so just the absolute value of F is integral rather than the absolute value of F squared, then again, there exists F bar in L1 such that F bar composed with T equals F bar. And most importantly, S and F over N converges to F bar. And here's the most important word in this theorem, is almost surely. Okay, and in L1. That's also true. So the upgrade here is not just to go from L2 to L1, which already would be some upgrade, but I think that the really big upgrade is that we go to almost surely. So again, what does it mean almost surely? It means that there is a set, X naught in X, such that it has full probability and such that, yeah, for every x in x naught, the limit, this limit exists of Sn of x over n exists. So this is the most important point of this theorem, that it's not just on average. So here, in order to say that the convergence in L2, you're taking the difference between this Birkhoff average and this function, and you take some integral of it. So there's some average, further space averaging procedure. So here there is no space averaging procedure. It means there is in your universe, okay, maybe you cannot predict the destiny of every point in your universe, but there is a very big space, like space of measure, full measure. Of course, the complement could be dense. I mean, topologically, things could be weird still. But from the probabilistic point of view, with probability 1, you take a point in here, and you take the iterate, and this average does indeed exist. So that's a big difference, because it's much easier, because you can, whenever you have to do something with the system, you can just take this generic trajectory, so this x that satisfies this, and this trajectory has all the good properties, and you can work with that without taking any integral. So, by the way, there's a pretty obvious corollary, because so this is called the ergodic theorem. So the system need not be ergodic, but you see, what do we get out of this is a function which is invariant. But now, what do we know about invariant functions for ergodic systems? They're only constant, right? So if t is ergodic, on top of that, well, then f bar has to be constant. And so, almost surely. So what this means is that, as a corollary, if the system is ergodic, you do this averaging procedure, and the result of the averaging procedure does not depend on the starting point. So for all, so there exists some c's, just some real number, such that for all x in x naught, this convergence, this average converges to some number. This number is a unique property of the system now. It's not a property of the starting point anymore. Yes.
Can one get Neumann's from Birkhoff?
Well, of course. I mean, especially from this one. So yeah, so there's two answers. So yeah, of course, if you converges in L1, so you will converge in L2, I think. But then the other thing is, yeah, you can integrate, right? This is almost sure convergence. Yeah. Now, if you do the by dominated convergence, basically, you can integrate on both sides. I mean, there is maybe some step in between, but basically that's no, that's strictly stronger statement. Yeah, still it's a bit unfair that this guy's theorem was not published because this guy didn't like him. So that was an interesting point. There's an interesting survey by Vitaly Bergelson about the history of ergodic theorem. Okay, now what's next? So this is by far the most famous version, but in our course, we will need often even a stronger version of that, which is the subadditive ergodic theorem, which is Kingman's theorem. So that's a bit later, in the 60s, I think, or like okay, so to look at the subadditive ergodic theorem, we have to look at the notion of a subadditive cocycle. So now we are not only talking about sums of, so you don't have a function anymore that you're just summing over a function, but you're summing something slightly more complicated than a function, namely a cocycle. What is a cocycle? So a cocycle, well, it is a function that traditionally we denote by a instead of f, but kind of plays a role of that. So it's a function from n times our space x to r. So now, instead of looking at the same function and looking at function today, tomorrow, and day after tomorrow, every day, so this n is the time parameter, every day we're allowed to change function, but change the function in a controlled way, otherwise there will be no. Okay. And it's subadditive, so a subadditive cocycle if, yeah, so if a, the following is true, so if you do a at the time n plus m, starting at the point x, this is less or equal than a nx plus a m t n x. So for every n and m, 0, and for every x in x. So you see, what is the subadditivity property? Is you look at the function at time n plus m. On the other hand, you can look at the function times n, and then from the point x, you see, wait, right? Yeah, so. Yeah, that's literally right. Yeah, that's right. So right. So what is going on here? So it's like I start at the point x. So and I apply the dynamics, and I get Tnx. And so the point is the cocycle at times n plus m starting from x is comparable to the cocycle from starting at x but from time n plus the cocycle from Tnx starting from m. So the obvious example is what we already saw. So if you do a n x to be f of Tnx, so the function after n steps, well, it's obvious. Now let's check, right? So what does it mean? What is n plus mx is f of Tn plus m of x. Sorry, this is the sum. Sorry, let's see. It's the sum. The sum of f composed with Ti from I equals 0 to n at x. So if you do this, this is the sum from I equals 0 to n plus m minus 1 of f of Ti of x. And this sum can be decomposed as the sum in the first n steps and the sum in the other steps. So this is the sum from I equals 0 to n minus 1 of f Ti of x. And then what? Well, the next one is the sum for the next steps from n to n plus m minus 1. Right, so if we call this S and f of x, as we just did before, well, you see that this, you literally have equality, not just inequality, but literally equality. right? So you have that this guy is what? Is S and F of X by definition, and this one is S and SMF, but starting from T to the N X. Right? And this is the same as S N plus N plus F of X. It's just a sum. So the cocycle notion kind of wants to model what happens if you're taking a sum over the orbit, but instead of having an equality, you can replace it with inequality. That's the difference. And now we can indeed study a similar thing. So instead of Sn here, right, now the new ergodic average will be the average of A and X divided by N. So that's the same type of ergodic average. And so let's state the theorem. So this is Kingman's theorem. So it says that if you let A be a subadditive cocycle, on the measure preserving system, so on X, A, P, T, a measure preserving system, usually before. And what do we need to assume? Suppose it's integrable, which means that A n for each n, the function an, the function as a function of x is in L1 for every n. So this is an integrability condition, and also we need to impose something that assures that the limit does not go to negative infinity. So the second condition is the following, is that the infimum over n or 1 over n, the integral of a n x dp x is bigger than negative infinity. Yeah, I mean, in practice, most of the cocycles that we're going to study are positive valued. So this is going to be trivial true. This is just to avoid that the average goes to negative infinity. Okay. Yeah, these are the only two conditions. So basically just an integrability condition. So then for almost every x in x, the limit as n goes to infinity of a n x over n exists. And again, more or less like what we described before, we can call this a bar of x. So if A is additive, so you have equality, this is literally the same as Birkhoff's theorem. But here we can replace additive with subadditive. That's the only issue, but it's a big issue. And again, A bar composed with T equals A bar. So it's also in there. And again, the good thing here is that if T is ergodic, A bar is constant for some reason. So if T ergodic, then A bar is constant. Almost sure. Any questions? Okay, so let's have a look at the most important example, in fact. So we will see the proof of this theorem, but before doing that, let's look at the most important example, that is the existence of drifts for random walks. So the application, the most important application to random walks, there are many, but certainly this is the first one. The application to random walks is the existence of the drift. And so what is the setup here? Well, the setup here is you take, again, let's take G a countable group, and mu a probability measure on G. Okay. And then once we have that, we can consider let omega p, this is the space that we defined as time, be the path space, meaning that the elements of omega are sequences, are the sequences W1, W2, W3 that represent the locations of the random walk. And P is the natural probability distribution that expresses the fact that you're actually doing this random walk. Okay, and then we assume, assume G, yeah, there is an action, G acts by isometries on a metric space that now, since we already had X before, let's call it Y, even though probably later in the course we will call it X in applications, but let's call it Y. So what does it mean? Again, that, you know, for each element in G, you can, and at every point in Y, you can define GY. GY is another point in Y, so that every element in G preserves distances in this metric space. Okay. Okay, and you take a base point. Let's call it small y in Y, base point, or some point. So the picture is picture that I drew many times, even though the base point we call it now Y, W1 Y, W2 Y, Wn Y, and so forth. Okay. So what do we want to look at? We want to look at the distance function, which is given by this metric space. Okay. So how do we look at the distance? Well, we define the distance cocycle. Okay, and how do you define it? Let's call it D and omega. So omega is an infinite sequence. So what is D and omega? Well, it's just the distance between the base point and the end step of the walk. So omega here means is a sequence. Is a point in this big omega. It's a sequence of random paths. It's the trajectory of this random walk. And yeah, you just take the distance between the end step and the first step, and like that. Just look at that. This is a metric space, so everything is well defined. So we don't need anything less. So the other thing is, okay, so is this a closed cycle and is it integrable? Well, so there's two things to check. So the first thing is that, yeah, we need another condition to make sure that it's integrable, and it is the following. So we define, we say the random walk has, so the random walk driven by, this is the usually means we start with G mu, has finite first moment if for some y in y, so what do? You take the distance between y and gy, and you're integrating with respect to mu. So, but this is a countable group, so we can even just say that the sum of this times mu g is finite. So you see mu as a measure on G. And yeah, and then you're taking the distance from y to gy, and you want this time to be finite. So what is the meaning of this being finite first moment? It means that, you see, this is the step length of the walk. So you do one step from y to w1. G is like w1. So the first step could, but on average, the first step has as this finite length. Because if in the easiest case, mu has finite support, so you have only finitely many choices, so that would be not a problem. But in general, you could have more than finitely many choices, but you just make it so that the average weight converges. Are there any questions? Can you actually see the board? Because everybody seems quite calm. Very calm, which is not a good sign, I think. So I don't know. I feel like the light is not so good, to be honest. Maybe we can. Okay, anyways, yeah, no, there's other questions here, because okay, so now what do you want to say? We want to say that this is a closed cycle. And to prove that there is an average, that this distance, when you divide by n, converges to a limit. So that would be the existence of the drift. Okay, so let me state it. So first of all, no one asked the question that everybody asks at this point. So this is not a good sign. Oh, yes, that's not the same question that I was expecting, but yes, that's a good question. Yes, so an example without finite first moment, yes, you could say that the probability that you see that, yeah, so let's say mu on z, so let's say g equals z. So mu of, right, 2 to the k equals 1 over k squared. The question is whether it's independent of y. That's right. So I'll tell you the answer. Yes. So yeah. So this is, yeah. So this would be an example, because so you see that you can make a really huge jump here with probability 1 over k squared. So you see what is the expectation of the drift. So you see the sum of mu 2 to the k times 2 to the k. So this is enormous. So this is a sum of 2 to the k over k squared, which is infinite. So it's possible, yeah, because you see, yeah, you can make enormous jumps. Of course, if you make reasonable jumps, then yeah, even well, in fact, even simpler. Also, you could say, yeah, even mu of k, I guess, because 1 over k squared still doesn't work, right? Because you take the sum over mu k times k is sum over 1 over k, and you still have it. So yeah, there are examples. So yeah, so the other remark would be that yeah, so if this holds for one y, it holds for every y. If star holds for some y, it holds for any y prime in y. So this is a good trick that I want to explain independently of this particular application. So you see what happens. So what's the difference? So if you take the distance between y prime and gy prime, this is not the same necessarily as the distance between y and gy, but you can do, there is a triangle inequality, right? So you can do, this is at most distance between y prime and y plus distance between y and gy plus distance between gy and gy prime. And now we can use the isometry property here. So you can remove the g because this is an isometry. So this is less than the distance between y, gy plus 2 distance between y and y prime. So whenever I give you y and y prime, yeah, so now if you integrate on both sides, well, this integral is finite. This is just a constant, does not depend on g. Right? Yeah, another way of writing this is to write the integral. This is like the integral of dy gy dmu g. So if you're an analyst, maybe you prefer this, but in the end, it's just a sum. So, right, plus, well, you take the integrate of this, but this integral with respect to a probability measure, so it's this. So the integral with respect of dy prime, gy prime, d mu g is less or equal to this. Okay. So, okay. So now let me state the proposition, which once you have the King-Lanzagodic theorem is not that complicated, but it's definitely fundamental proposition. And you talk about random walks and groups, which is the following. So let G mu, again, a group with the measure, so we call it a measure group. And this is acting by isometries on a metric space on Y D. So if the first the finite is the first, if the first moment is finite, so you see the first moment is a property of all these things, in fact. because it depends on the measure, because you're doing the integral, also depends on the distance. I mean, you could have a group that act on different spaces, and on different spaces, the first moment could be finite or not, depending on the type of action that you have. But given these two things, you can say if the first moment is finite, then there exists some L. This is a constant, could be 0 or positive, such that for almost every omega, so sample path, yeah, so the limit as n goes to infinity of the distance between y and w and y divided by n equals this number L. So you see, this is the first property, the first numerical characteristic, the first number that is associated to a random walk. Because this number does not depend on the path that you're choosing. Well, again, it does, but for a full measure set of paths, you get always the same number. Okay, so the definition, so we call L the drift. So I usually use the name drift or rate of escape or speed. In fact, it's literally just the speed of the random walk.
Do we know anything about the spectrum of L depending on the group?
That's a very good question and not an easy question at all. But yeah.
Like in the hyperbolic.
So there are cases where people can say, oh, for every L, you can find a random walk. There are theorems like this.
I meant rather like, is it rational?
This number is extremely rarely a rational number. Yeah, the relation between L and the generators is extremely complicated and transcendental. I mean, yeah. I mean, we'll talk more about that. But I mean, in general, computing L is really hard. I mean, numerically, for say like matrices, there are good computer programs like algorithms that can give you this number at up to many digits, but you're not expected to find a closed form for this L.
So the reason I asked her last thing is, for example, measurements are always
I understand.
rational.
Yeah, but here you're combining different elements with different axes, so that things are not aligned. So it's complicated, but yeah, I think there are some not trivial theorems at all that they might say, okay, maybe if you fix G, and for every L, you can find some measure mu that maybe gives you this as a drift. And in certain conditions, I think these theorems exist. But yeah, so L is a function, as I said, is a function of many things, notably both of mu and D. So if you change either of those, L can change. But at least the one characteristic which is a bit more robust would be whether L is 0 or not. And this is already a very important distinction. Okay, so we can prove this proposition given the theorem. So that's not so complicated. Okay, so the proof is, again, we show that this cocycle is additive, is subadditive, and integrable. So again, we take d and omega as distance between y and w and y. Okay, I want to say that is a subadditive cocycle. So how do we show that? Remember, what is the dynamics here? So remember, so with respect to, so the system is omega p, and t is the shift. T again is the shift in the space of increments. Remember, this is the important thing. T is the space that shifts the g's, not the w's. So this is shift of increments, because otherwise it's not true. So the thing is, again, the measure preserving nature is true for this shift. Okay, so now literally we just apply everything. Okay, so what do we need to prove? We need to prove that dn plus w n plus m w is less or equal than dn omega plus dm pn omega. Okay, let's write it. So this is the distance between w n plus m y and y, basically. The question is less than the distance between w and y plus what? Okay, so what is going on here? So if you think about it, so you have omega. Let's write it as g1. Let's look at the g coordinates. So we are shifting by n steps. So this is gn plus 1, so forth. So we are applying t, so we are shifting this. So Tn omega starts from gn plus 1 up to gn plus m and so forth. So what are we doing here? And what is w? W is the product of the first, however, of them. So this literally is the following, is the product of the first n m entries of this new sequence. So this is g n plus 1, g n plus m, acting on y. You see, this is what this operation is. So that's the interesting part, because somehow it's not, it's very nice, because it literally just works, but yeah, it's not, it's not hard, but somehow all the pieces of the puzzle fit together. So let's see. So why is this true? So is this inequality there true? So why is it true? So what do we need to use? We need to use two things, actually. Yeah, the triangle inequality seems always to be useful. And also here, yeah, exactly. So we want to use the fact that we are acting by isometries, right? So you see, okay, we can rewrite this exactly like that. Or yeah. And this one, since this is isometry, we can multiply by Wn on both sides. So if we multiply by Wn, which is G1 Gn, we have G1 Gn, right? So you have G1 Gn, Gn plus 1, Gn plus m, y, and then here G1 Gn, y, like that. And so this is literally dWn y plus dWn plus m y Wn y. And of course, this is bigger than distance between Wn plus m y. Why? This is literally the triangle inequality. So this one just works by using the two things, the triangle inequality and the fact that this group is acting by us. Okay, the second thing is the subadditivity. By the way, let's remark the other thing. Suppose that if the cost cycle is positive, so an of x is positive for every n and for every x, which is the case for this drift, for this distance, because distances are non-negative, then it is enough to check that A1 x is in L1 to show A and x is in L1 for every n. So why is that? Yeah, by the subadditivity, because what? Because yeah, by induction, because think about this. So if you do A of n plus 1 x, this is less than A n x plus A1 T n x. Now, if you integrate on both sides, so if you integrate in dp on all sides, now we observe that exactly that p is t invariant, so we can kill this t, right? So this would be integral of a and x dp plus integral of a1x dp. So by induction, if we know that this is finite, then okay, we start with n equals 1. This is finite, and this is finite, and so forth. So by induction, the integral of a and x dp is finite for every n. So that's okay. So now why is a1 integrable? Well, in this case, if you do the integral of a1, which is d in this d1 omega dp omega, this we have to check. Well, what is this? Well, this is the integral of dy w1, or yeah, w1y dp, let's say like this, in omega. So this you're integrating with respect to omega, which is an infinite sequence, but this function only depends on the first entry, right? So what's the distribution of the first entry? Well, it's mu by definition. So this is the same as the integral over g of dy gy d mu g, and this literally is the definition of finite first moment. Yeah, finite first moment. Okay. So we are good. So we are good because we have showed that we can apply the Kingman's theorem. So by Kingman's, the limit for almost every omega, which is an infinite path, the limit as n goes to infinity of distance between y, w, and y over n exists. We can call it L of omega exists. Now, the other thing we just have to realize is indeed that this is a constant. And why is this a constant? Yeah, by ergodicity. But since T with the shift is ergodic, there exists an L constant such that L equals L of omega almost sure. So that's it. So this proof is not so complicated, to be honest, but it's a good way to see that you really, and you see already that, the way we're acting, already we see why we're multiplying elements from the right, but we're acting on the left, which seems a bit counterintuitive, but already in this first example, you see that if you did the opposite, then you would have, you would have a bigger problem because you cannot even apply this. Okay, I guess it's actually time to stop, so why not? So we started at 10, so yeah. Okay, perfect. Are there any questions?
Yeah, so like here, like it's kind of like the metric space is not part of the dynamic system, right?
No, the dynamical system is just the space in the group. Yeah.
It's kind of weird.
Well, there are two dynamics, right? There is a random dynamics on the group, and there is a dynamics of the group action. Yes. So both, of course, are useful, but yeah, for this theorem, we don't use the dynamics of the group action, and that's good because this means that the theorem is always true. Otherwise, you would have to use more sophisticated properties of the group action, which we will at some point. For instance, if X is a hyperbolic, if Y it would be a hyperbolic space, then you can show L is positive. Otherwise, it's not going to be true. So for example, yeah, good. No, we didn't. It's not hard to prove, but yes. Yeah, you can think about it. Yeah, it's not that hard to prove. No, I agree with you. Yeah, by the way, on Monday at 5, I said that I would have office hours, so if you're interested. On Zoom, I put on the portal the Zoom link, but I think you should be able to see it. Okay, good. So see you next week.